Hi guys, welcome to the today's session of design and analysis of algorithms. In this session, we are going to discuss about module 12, which explains about transform and conquer algorithm design strategy. So in this module, we are going to discuss about three topics. Those three topics are heaps and heap sort, Horner's rule, and problem reduction. Problem reduction is a small concept. Now here we can majorly concentrating on these two, heaps and heap sort and the Horner's rule, right? Now, as part of today's session, we are going to see heaps and heap sort. So here in this heaps and heap sort, we are going to explain what is a heap, what are the types of heaps, and what is meant by heap sort, how we can perform sorting using heaps. Those things that we are going to discuss. So first, what is meant by a heap? Right. A heap is a binary tree with keys assigned to its nodes provided following two conditions. What are those conditions? Tree's shape requirement and parental dominance requirement. These two conditions, a tree with keys which is satisfying these two conditions is to be called as a heap. Right. Now, what is meant by this tree's shape requirement? The binary tree is essentially complete. All its level is full except possibly the last level where only some rightmost leaves may be missing. Generally, how a binary tree can be represented? What is a binary tree? A tree with at most two childs at any node is to be called as a binary tree. Right. That is, for example, here I have the root node. At most two childs should be present for this. So here, if it is having two childs, it can be represented as this one. Now, if it is having two childs, it can be represented as this one. If it is having two childs, it can be represented as this one. Now, here I am saying that this is having only one child. This is represented as like this. And this is having also only one child. It can be represented as like this. This is to be called as a binary tree. Right. So here it is having two childs, it is having two childs, it is having two childs, it is having one child, it is having zero childs, it is having one child, and it is having zero childs. You can observe that at maximum. Here this is also having zero childs, this is also having zero childs. If you observe any node, at any node, it is having either zero childs or one child or two childs. So that's why it is to be called as a binary tree. Right. Now, what is a complete binary tree? Complete binary tree means all levels should be filled completely. This is to be called as a complete binary tree. Right. Since both left child and right child are present. Now, is this becomes a complete binary tree? No. Why? Because this node is having two childs. In the same level, this node is having zero childs. So that's why it is not to be considered as a complete binary tree. Now, if it is having this child, now is it becomes a complete binary tree? No. It is having only left child. For making it complete, it should also have right child. This is to be called as a complete binary tree. Right. So, tree shape requirement means essentially it should be complete except possibly at the last level where only some rightmost leaves may be missing. So here to make it a heap, possibly I can remove the rightmost tree. Except this rightmost leaf, remaining all should be filled. Then it should be called as a heap if it is satisfying this property also. Right. What is this property? The key at each node should be greater than or equal to the keys at its children. Definitely, here suppose for example, here I have a key 7, here I have a key 10, right? The key present here should always be greater than its childs, right? Here, suppose I can represent the key 8, it not becomes a heap since its parent is less than it. So here, if it is present as 5, I can consider it as a heap. Here, this is 6, let us say, and this is, what is this? This is 9, let us say. right? This is to be called as a heap, right? Now, here you can see the example for heap and not a heap. One example I given which not becomes a heap. One example I given which becomes a heap. So here you can see this is satisfying tree's shape requirement. So it is a binary tree and the tree's shape requirement is present, as well as all the keys. If you observe all the keys, their parents are either equal or greater than the parents are greater than the child nodes. But here you can see this cannot becomes a heap. Why it not becomes a heap? Here I can miss the last level. In last level, I can miss some rightmost leaf, but not the leftmost leaves. So here it misses the left tree. So tree shape requirement is missing here. Tree shape requirement is missing. So that's why I cannot call it as a heap, right? So this is a heap. This is not a heap, right? I hope that you all understood what is a heap. A heap is a binary tree. It is assigned to its nodes, which should satisfy the tree's shape requirement as well as parental dominance requirement. Both the properties are satisfied, then it is to be called as a heap, right? Now, important properties of heap. What are the very many important properties of heap? So there exists exactly one essentially complete binary tree with n nodes, whose height is log n. Okay, there exists exactly one essentially complete binary tree with n nodes. Suppose if there exists a complete binary tree with 3 nodes, then its height is definitely to be represented as log 3, right? Its height is definitely to be represented as log 3. Next, a heap can be implemented as an array by regarding its elements in top-down or left-to-right fashion. Here I can represent the elements in the top-down way if the array is present like this. If the array is present like this, I can represent the elements in this fashion, left to right. Right. Now, how these elements are represented in the array? The parental node keys will be in the first n by 2 positions, while the leaf keys will occupy the last n by 2 positions. So here you can see the example for this. This is the heap. What are the parental nodes? 10 is a parental node, 5 is a parental node, and 7 is a parental node. These 3 parental nodes are present at first n by 2 positions, whereas leaf are present at last n by 2 positions. So here you can see the first n by 2 positions are filled with the parental nodes, and last n by 2 positions are filled with the child nodes, leaf nodes, right? Now, here one more thing that you can see regarding this representation, array representation. The parental position I, if 1 less than or equal to I less than or equal to n by 2, will be in position 2i. Suppose if any parent is present at n by 2 position, if that n by 2 position is represented as I, then its child is present in a position either 2i or 2i plus 1. Suppose here 5 is present in the position 2. Now I is equal to 2. Now the child of 5 is present in either 2 into I position or 2 into I plus 1 position. That is 4th position or 5th position. Now let us see 5 children, 4 and 2. 4 is present and 2 is present, which are present in 4 and 5th positions. Like here you can see 4th and 5th positions. Right. Now correspondingly, the parent of a key in position I will be present in the position I by 2. Right. So here, any key, if it is present here, if any node, a child node is present in the position I, then its parent will also be present, always be present in the position I by 2. That is 5 by 2 position. What is 5 by 2 here? I can represent it as 2 by 5. When I am rounding up, its value becomes 2. Now its parent is present in the 2th position. Now 2 parent is 5, which is present in 2nd position. Right? So if parent is present in the ith position, then its childs are present in either 2i or 2i plus 1 position. If child is present in ith position, then its parent is present in definitely I by 2th position. Right. So these are the major properties of heaps. Right. Now here you can see types of heap data structures. Generally we have two types of heap data structures. One is max heap and another is min heap. What is meant by a max heap and what is meant by a min heap? Let us see. In a max heap, the key present at the root node must be greatest among the keys present at all of its children. So the key present at root node must be greatest among all the keys which are present at its children. So here you can see the example for max heap. Here all this is a max heap because the root node value is 100, which is greatest among all its children. Right. Now, what is a min heap? Min heap is one. In min heap, the key present which is present at root node will always be minimum among the keys which are present in children. Okay. So the key value which is present at the root node should always be less than that all its childs, right? So here you can see that min heap. So here 10 is the key present at root node, which is less than all of its childs, right? This is to be called as min heap. These two are the max heap and min heap. Next, coming to heap construction, how a heap is constructed, right? Now here there are two approaches for constructing the heap. One is top-down construction and another is bottom-up construction. Now here we are going to see both the methods, how a heap is constructed using top-down way and in a bottom-up way. Let us see here. Given the keys are 2, 9, 7, 6, 5, 8. Now in the top-down approach, how the heap is constructed. First we need to take the key 2. First we need to insert the key 2 into the empty tree. Next, we need to insert 9, right? Now, when I am taking 9 initially, 9 becomes the left child. First, we need to fill the left part, then we need to fill the right part. So that's why first 9 comes here, right? So after that, since it is not satisfying the property of parent dominance, I need to rotate it. 9 becomes the parent and 2 becomes the child, right? So, first 2 and 9 are added. Next, I need to add 7, 6, 5, 8. Now, first I am going to insert 7. Already I have 9 too. 7 definitely becomes the right child. First I fill the left child, then right child should be filled. So here 7 is correctly present, right? It is satisfying the binary tree property as well as parent dominance property. Next, I am going to insert 6, right? 6 should be the left child of this 2. Definitely first left child should be filled, then right child should be filled. So that's why insert 6. 6 is present here, but it is not satisfying the parent dominance property. Here 2 is a parent, it should be dominant. So that's why I am doing rotation. 6 comes to here, right? Next, I need to insert 5. 5 should become the right child of 6. First, after filling the right child of 6, then only we go for the 7, right? Now 5 comes to here. Now it is satisfying both the properties. It is a binary tree and as well it is satisfying parent dominance property. Next, I need to insert the next element, which is nothing but 8, right? Now 8 becomes the left child of this one, but here this is not satisfying the parent dominance property. So this to be rotated, 8 becomes the parent and 7 becomes the child, and finally this becomes the heap tree which is constructed using the given keys. This is the top-down approach. Now, what about the bottom-up approach? In case of bottom-up approach, initially we consider all the keys according to the order that they present. Now, my keys are present in the order. So, in which order my keys are present? Let us see that order. 2, 9, 7, 6, 5, 8. Right. Now, here you can see 2, 9, 7, 6, 5, 8. Now, how I am going to construct a heap? 2, 9, 7. Now, here I am not satisfying any property. I am not checking for the properties. First, I am going to construct the tree in case of bottom-up approach. Later, I will check. After filling C, 9, 6 comes here and 5 comes here and then 8 comes the left child of 7. This is the tree, right? When we are taking orderly the representation, right? Like this, first we need to construct the tree. So after that, we need to check heapifying process, whether it is satisfying those properties or not. That I need to check. Now, I'm going to compare here 7 and 8. Since it is not satisfying the dominance property, parent dominance property, these two are to be rotated. Now, after rotating these two, this becomes like this, right? So after this, again, I need to compare 2 and again, I need to compare these two. So when I am comparing, next I need to compare 9, 6 and 5, 9. So when I am comparing these two, these are satisfying the dominance property. But when I am comparing 2 and 9 and 8 and 2, these are not satisfying the dominance property. Since these are not satisfying the dominance property, now for making to satisfy dominance property, 9 becomes the parent and 2 becomes the child. Again, I need to check these two also. These two are in the correct way. So that's why the final tree, heap tree that I get from the bottom of approach is this one. So I hope that you are observed the difference between top-down approach and bottom-up approach. In case of top-down approach, we one by one we add the nodes, and at every step we go for checking heapifying, whether they are satisfying the condition or not. We are checking. But in case of bottom-up approach, initially we construct the tree. After that, step by step, we are going to check and we are going to heapifying, whether they are satisfying the properties or not. We are checking, right? So I hope that you all understood how to construct a heap using the given keys. Next, coming to the operations of keys. Here we have given some basic operations, standard operations that can be performed on heap: get min, extract min, decrease key, insert, and delete. These are the major and standard operations that can be performed on keys. Now, what about these operations, standard operations? Now, we are going to see these operations one by one. So, first one, get min. It returns the root element of min heap. It returns so first one, get min. It returns the root element of the min heap. Since always the minimum value is present at the root node in case of min heap, so that's why it returns the min heap. But if for the max heap I want to use, I need to use the function get max. I need to use the function get max. For max heap, it returns the root node. Next, extract min. It removes the minimum element from the min heap. Here, minimum element is nothing but in case of min heap, the root element. The root element can be removed from the heap. Next, decrease key. It decreases the value of the key which is present at any position. Okay, so any key value may be present at any position. The value of that key can be decreased. Next, insert. It inserts the new key values into the tree. So insert operation inserts the key at the end of the tree. At the end of the tree. So after that, it is going to be checked for heapifying. Right. Next, delete the key. Deleting a key which is present in my heap tree. That is to be called as delete operation. Right. So all these are the standard operations that can be performed on heap data structure. Right. So I hope that you all understood about heap data structure. Now, based on this heap, we can do sorting as well. Next, we can see heap sorting. Right. Now, here you can see heap sorter. It is a comparison-based sorting technique based on heap data structure. So, heap sort basically recursive performs two main operations. What are those two operations means? First, building a heap H using the elements of array and repeatedly delete the root element of the heap formed in the first phase. Right. So, first we need to build the heap and then we need to remove the elements one by one in the next steps. Right. Here you can see an example, or here you can see first algorithm steps in that heap. So first convert the array into heap data structure using heapify. Then one by one delete the root node of the max heap and then replace it with the last node in the heap. Then again heapify the heap. Repeat this process until the size of the heap is greater than 1. Right. Now here the same steps are represented here. Let us see. Build a heap. Next, repeat the steps. What the steps I am going to repeat? Swap the root element of the heap with the last element of the heap. remove the last element and heapify, then sorted array will be represented in the reversing order, right? These are the steps that we need to follow for heap sort algorithm. So here you can see detailed working of heap sort algorithm. So here I have given an array of elements. Now with this array of elements, first I am going to construct a heap. Now how I am going to construct a heap? 4 is the root node. The left child is 10, right child is 3, 5 is the left child, again 1 is the right child. Right, like that first we are constructing a heap, but transform it into max heap. Now I am going to transform it into max heap. So for making it as max heap, the maximum element should be present at the root node. So that's why I need to send 10 to the root node. So here I send 10 to the root node. Now 4 becomes the left child of 10. But here heapifying property is not satisfying. That is parent dominant should be satisfied. That's why it should be moved to here. Now final tree after max heapifying. This is the final tree what I am getting after doing the heapifying to construct the max heap. So after this, what I need to do is I need to remove the maximum element and which is to be inserted at the last element should be inserted at that place. Now 10 is removed from here. Now 1 is the last element which should come here, right? But here it is not satisfying the heapifying property. So that's why 5 goes here, 4 goes here, 1 comes to here, right? Now this is the max heap that is remaining. Now 10 is removed from the processor. Now 5 is to be removed. To the 5 place 1 comes here. Now when 1 comes here, it is not satisfying again heapifying property. So 4 comes here, 1 comes here. Next 4 is removed. Right, when 4 is removed, I got 3 and 1. Next 3 is removed, next 1 is removed. Now once the elements removed are 10, 5, 4, 3, 1. In this order, the elements are removed. Now you need to reverse this. I'll get the sorting order of the given elements. Right. So this is the process of sorting the elements using heap data structure. I hope that you all understood what is a heap, what are the types of heaps, what the operations on heaps, and how to construct a heap, and how to do the sorting using heaping. So all those things explained. So I hope that you all understood. Try to solve some more problems, then you can understand better. Thank you for listening. Thank you.